Okay. So let me begin. It's now being recorded. Okay, let me begin again. So if you have simple linear regression, it means that you have one DV and one IV. Okay, so your population model will be given by this one, and your estimated model based on your sample data will be y hat equal to beta naught hat plus beta 1 hat x. That's it. Or sometimes you can see they use a small letter beta naught plus beta 1 x. Okay, either one, but I usually use this one. Okay, so now from this simple linear regression, we can study about the R. Okay, we have R, which is the correlation value. Okay, can you still remember? Do you still remember what is correlation value? What is the range for R? What is the range for R? The range value for R? Class? R can take value. The least is what? The least is what? Anyone, please? What does the correlation value begin with the value? What will be the value? Anybody? Give me the range of the R value. Class, someone, please. Hurry up. Hurry up, please. What is the minimum value of R?
-1.
Yes, -1, and the maximum value can be?
1.
Yes, +1 or 1. Okay, so the middle is 0. So what does -1 means? Strong. So if you can still remember, what does this value tells you? R tells you the strength and the direction. So direction either negative or positive. If negative, you have this equation, or scatter plot will be look like this one, or positive, you will have this one. So what about the strength? -1 and +1 is what we call as strong relationship, be it for negative or positive. So strong negative relationship looks like this one. Strong positive relationship will have this particular form. And then when we say strong, what do we mean by strong? Okay, if I can draw somewhere over here. If let's say I have a scatter plot, like for example, this one, and a scatter plot compared to this one. Now, which of these plot, A or B? So this is A, this is B. Which of the plot that show strong linear relationship, A or B?
B.
Why? Why B? Why B? Because when you draw the line, okay, compared to this particular scatter plot, you can see that the line for this one, the distance of this particular point to the line compared to this one, okay, this one is much bigger, okay, compared to this one is smaller. smaller error. This one, bigger error. So that's why you will have what we call strong linear relationship will be defined by this particular scatter plot, not this scatter plot. So this one is very strong linear relationship, positive. Okay, positively. So, and remember back, this one will go back to your least square, the least square method. Okay, the least square method is a method whereby you can minimize the error between the points with the predicted line. This one. Okay, so that will be among the things that we have covered previously. And we also discuss on the R. Okay, on the R squared. That is the coefficient of determination. So what is coefficient of determination? How much, oh my goodness, how much X explain Y. That is the simple way, okay, on how you can describe the coefficient of determination. Okay, how much X explain Y. If you are talking about variation whatsoever, you can go into the full definition of what is coefficient of determination. And we have seen how we can perform the hypothesis testing for the correlation and the hypothesis testing for the model using either the T test or the F test or the based on the ANOVA. Okay, so we have gone through that in the previous class. Now, what happens if you have more than one IV? Means that right now you are having more than one IV, whereby you may have maybe two, three, four, depending on the needs of your modeling. So this is what happened for multiple linear regression on how we can write down the estimated model. So this is what we call as the estimated model. Estimated model. So you can see over here, when you see this, you should think right away when you see this will be based on the sample data. Okay, so when from the sample data, obviously they are much similar to what you have in the simple linear regression. It's just that you have more than one IV. So this is the first independent variable, the second independent variable, and the kth independent variable. So in the case of multiple linear regression, as long as you have two or more independent variable, so we call that as multiple regression, or sometimes we call it as multiple linear regression, which is more correct in terms of describing the model, since we don't have any quadratic equation or quadratic form in the equation. Now, what you should know about multiple linear regression? I believe if I were to teach this in the undergraduate level, I would discuss in a further what we call a more systematic and structured way on how I can explain the multiple linear regression. But since you are in year one and semester one of your program, so I guess the need to simplify on the modeling part is being used here. So that is why some of the things that sometimes necessary for you to know is not being discussed in this particular slide. So if you read your textbook that you have with regard to multiple linear regression or multiple regression, you can have more than what you more discussion from what you have in the slide actually. So please understand the way the slide is being presented is the simplest way, so that it fulfill the requirement for you as the first year students and first semester student for principle of data analytics. So everything is being simplified for you. But the dangerous part of being simplifying too much, you may lose some part of the, the backbone of this particular model. So I really hope, even though the slide is a bit too simplified, you can go back and read on your own, source for the multiple linear regression, so that you can have more understanding on this particular model. Okay, so if let's say you have any problem along the way, please let me know and I will just explain to you again. Okay, let us see. Based on this particular estimated model, okay, you have one IDV and you have multiple IV. Okay, so in this case, let us see one example. Okay, if we are talking about the example of home price versus bedroom, so we are talking about the price, which is your Y, okay, and your number of bedrooms is your X. Okay, so in a random sample of 1057 homes, can bedroom be used to predict price? So if let's say this is the example, and this one is taken from Zillow.com. Unfortunately, in this slide, we don't have the actual data, but the data is being described in terms of the five number summary or box plot. And we can see over here, we have what we call multiple box plot to compare uh, based on the number of bedrooms. So if you can see over here, the number of bedrooms, you can have one bedroom, two bedrooms, three bedrooms, four bedrooms, and five bedrooms. And based on the price, okay, based on the price, you can see for one bedroom, the box plot is very small, or very um, the range of the value or the price of one bedroom is very small compared to more bedrooms. For example, in this case, five bedrooms, you can see that the price for this particular home is very uh, widely spread. Okay, you can see that among the five bedrooms, you can see five bedroom has more variability in terms of the prices. Okay, can someone tell me why more bedrooms have what we call I'm trying to change my setting. Okay, why five bedrooms have more variation in terms of the price? Can someone tell me? Just a common sense questions. And what will be your common sense answer for this particular scenario? One bedroom, the price is not as varied as compared to five bedrooms. Why is it so, class? Someone, please. We have discussed this. We have discussed this in the first chapter on the exploratory data analysis. When we have box plot, wider spread and smaller spread, what can you have in your mind for this particular scenario? Anyone? If let's say for one bedroom, if you are talking about in terms of the demand for one bedroom is smaller compared to the demand for five bedrooms. For example, if you are talking about the community, whereby we are talking about the community which is not in the urban, if you are talking about a small town, so five bedrooms, how home with five bedroom is more demanding compared to one bedroom. That is why the prices for five bedrooms home is very depending on the maybe depending on the developer, the location of the house, and of course uh, it goes back to the maybe other part of the uh, home, which is maybe 5 bedrooms, bigger square feet of bedrooms will be more expensive compared to a bedroom with standard size. Okay, so that will be among the things why this become so big in terms of the variation. Okay, as compared to 1 bedroom, whereby the demand will be much smaller and less people is buying home with 1 bedroom compared to more than 1 bedroom. So that is why that will be one part on, or one way on how you can interpret this particular scenario. But when you go back to the relationship between home and number of bedrooms, okay, so you can see that obviously here we can say approximately that the linear relationship between the home price and the number of bedroom is linearly related. So it means that if you are talking about um, less room, the price will be smaller. More rooms, the price will be much higher. Okay, so that will be one way on how you can interpret that particular positive linear relationship. Okay, so equal spread condition is violated. So in this case, you can see that for each number of bedrooms, okay, the spread is different. Okay, so that is obviously can be expected from this particular side by side box plot. And be cautious about using inferential method on this data. So one things that you have to remember back when we are talking about the assumption for simple linear regression about the distribution of the distribution of your data, or the variance of your data, it should be equal, so that we can have what we call not biased, what we call interpretation. So this could be something that you need to ponder before you go for the analysis. Now, for simple linear regression, for in this case, home price versus bedroom, okay, you can see that the R squared in this case is 21.4%. Means that the number of bedroom can only explain the variation of the home price only by 21.4%. So this is your correlation coefficient of determination. Okay, class? So for the coefficient of determination with the value of 21.4%. So this one already in percent. So in the original data, so it will be 0.214 in terms of the value. So R squared range from 0 until 1. R from -1 until +1. So remember that. So 21.4% for R squared. Is it good or not? Is it a good indicator for the home price? Does bedroom is a good independent variable for home price? Yes or no? Class?
No,
Bedroom? What was that?
no,
No. Why?
because it's far from one.
Yeah, it's very small. Okay. The nearer it is to 100, if you are talking about 100, the nearer to 100, the better the variable is to your dependent variable. So in this case, bedroom can only explain 21.4% in the variation of home price. So in this case, bedroom, if you're relying on one variable, independent variable, means that bedroom is not the correct independent variable. But, okay, but you can perhaps include another factor into your model so that you can predict home price not only based on the bedroom, And in this case, it could be another variable or independent variable that can help us in terms of making prediction on the home price. So let us look at the second one. Now, in the second model, okay, we include the living area. Okay, living area is the ruang tamu lah. Okay, so this is where we call this as multiple regression, whereby we have our Y is the home price, X1 is number of bedroom, or simply call it as bedroom, and X2 is the new variable, which is living area. So living area, let's say just put it as, call it as in unit, okay, whichever the unit is. Okay, in this case, what happened to the R squared? Okay, the R squared consume about 57.8%. By adding a new variable into your model, which is the living area, okay, the coefficient of determination increases to 57.8%. Means that by adding, by having bedroom and living area, okay, they count about 57.8% variation in the home price. Okay, in terms of R squared, it is increasing, which is much better than having only 21% of the R squared by having only bedroom. Now, in the previous slide, if you can see, by having the bedroom, even though the R squared is very small, it shows that this particular variable is significant. Oh, sometimes this is rarely happen. If it is significant, most of the time, this R squared value will be higher in the value. But in this case, this happened the other way around. Okay, even though if you can see that this particular variable is significant, means that bedrooms and home price is having a linear relationship between the two. But adding the living area, okay, we can see that what happened to the p-value. Okay, does the living area significant to the model class? If let's say alpha is 0.05, is living area significant to the model? Yes or no? When I say significant to the model, it is important um to the home price by evaluating single predictor to the Y. Does living area significant or not, class? Significant means that living area is importance to home price. Important or not important? Hello, class. Please, you can try. It's okay. Whether it's correct or wrong, I don't mind. Just respond to my questions. Is living area significant to the model?
Not a day.
Class, why no? Why no? Alpha is 0.05. Yet your p-value is smaller than alpha. If smaller than alpha means what? We reject the null hypothesis. Reject that living area has no relationship with home price. So in this case, we reject the null hypothesis, means that living area is not equal to 0. Means that living area has linear relationship with multiple regression. The same goes to bedroom. Bedroom is 0.007. So 0.007 is smaller or bigger than 0.05? Class?
Yeah.
0.007 is smaller or bigger than alpha?
Yes, smaller.
Smaller. So means that it is significant. So means that we reject the null hypothesis, shows that bedrooms has significant relationship with the home price. Okay, or with the model. So in this case, now the model account 58% of the variation in price. And based on the evaluation of each of the variable, both are significant to the model. Now, what happened next? For each predictor, what do we call predictor? The predictor is X1 and X2. That is the bedrooms and the living area. Okay. For each bedroom and living area, regression output will show a coefficient, its standard error, T ratio, and the corresponding p-value, as what we have seen over here. Okay. T ratio and the p-value and the standard error over here. Now, as for now, I only want you to understand about the p-value. Okay, with regard to the multiple linear regression or multiple regression. Okay, the T ratio measures how many standard error the coefficient is away from zero. The T ratio. Okay, how many standard deviation it is away from the zero. So if it is further away from zero, means that it is bigger. Okay, either negatively or positively. Okay, so in this case, you can see the bedrooms in terms of the value is um, a negative 2.69, and for the T ratio is 30.18. Okay, and we can use the p-value to test each coefficient is different from zero, as what we have discussed just now. Okay, so that will be on how we can interpret the every single IV or predictors in your model. Now, the meaning of coefficient in multiple regression can be subtly different than in regression, simple linear regression. Okay. Okay. Now, what happen if if I use the previous example, y hat is equal to the first model. This only, 14349.5. That will be the coefficient. Hold on. So in this case, it will be y will be equal to 14,349.5. That will be the interception plus 48,219.9 x. So this one is your bedroom. This is your home price. Okay, what happened is that when you interpret the coefficient, I think last time I forgot to discuss on this. Okay, now interpreting the coefficient. So this is your coefficient of your beta 1 hat. So in this case, your beta 1 hat is equal to 48,219.19. Sorry, 0.9. Okay. So in this case, how do we interpret? Okay. Y, or if I can say using the home price. Okay. This is for one simple linear regression. Okay. As number of bedroom increases, home price is increases. Why, class? Because look at this particular what we call sign over here, plus. That is why it shows, shows an increase. Okay, by having the number of bedroom increases, okay, as X increases, Y also increases. So in this case, as number of bedroom increases, home price is also increases. Okay, so that is how you can explain on this particular example. If let's say here is negative, okay, as then you can say that as X decreases, okay, Y may also decreases because you have this particular value over here is negative value. Since this coefficient is positive, so it will be easier for you to what we call to interpret. But for negative value, it would be based on you need to see on the actual facts for this particular example. And later, if I have a specific example with regard to negative value, it would be easier for me to explain to you. As for now, please understand this is how you can interpret on in terms of the meaning of the coefficient. That will be on how on the single coefficient. Now, what if you have multiple linear regression or multiple regression? In this case, you have bedrooms and you have the living area. Okay. So in this case, on how you can interpret, we can describe this in terms of if let's say we take into consideration home in sample with the living area in terms of unit from 2,500 unit if the square foot up to 3,000 unit in terms of the living area square foot. Okay, as you can see over here, okay, for 3 number of bedrooms, the variation in terms of the prices are even bigger compared to 4 bedroom and 5 bedrooms. Okay, so you can see over here, as we increase the number of bedrooms, the prices in terms of the variation decreases. Okay, so in a multiple regression, each coefficient takes into account all other predictors in the model. So in the case of this one, if you are interpreting this particular bedroom coefficient, okay, what happened is that you have to make this as constant. Interpret this, so this one will constant. Okay, if you interpret this, you need to make this as constant. So that is how multiple regression works. Okay, so we can only interpret one coefficient based on one single IV, taking into consideration the rest of the IV is constant. Okay, so in this case, for houses with similar size living area, more bedroom means smaller bedrooms. Imagine you have the same square foot of a house, okay, but talking about more rooms and versus the living area. So if you want a bigger living area, okay, so you may have let's say we divide into this one living area, this one will be your room, so one room only. So this one may be a kitchen, this one may be something else. So if let's say you want to add more rooms, okay, more rooms means that you will have to decrease the living area unit. Okay, so this is your living area. As you have more rooms in your house, so you will have smaller living area. Okay, let's say this is the kitchen and this is, let's say, the store. This is the store. So just to give you an idea, how does the living area uh, give an impact to the number of bedrooms in a house, and that will impact the price value of that particular home. Okay, so I hope you can understand on that. So means that more bedroom means smaller bedrooms and or smaller common living space. Means that we have to cram room, make decreases the value of a house. Okay, so more bedrooms means that you will have to decrease on the value of the house. Less bedrooms, okay, so the price might be higher. Okay, that will be on how we can interpret the meaning of the coefficient in terms of the, in the what we call the IV in your model. Okay, so what the correct answer to the question? Do bedroom tend to increase or decrease the price of a home? Okay, so correct answer, price tends to increase if bedrooms is the only predictor. Okay, price may increase if bedroom is the only predictor. Okay, means that more bedrooms may mean bigger house. Okay, and price tend to decrease if bedroom increases for fixed living area. So you can see over here. Okay, see, the coefficient of bedroom is negative, the coefficient of living room is positive. Okay, so for the bedroom is negative, means that price in terms of the bedroom, okay, price tend to increase if bedrooms is the only predictor, but price tend to decrease if bedroom increases fixed for living area. More bedroom means smaller or more cramped rooms. So this is for single, and this is for multiple regression. So means that price tend to decrease when you have this. Why decrease? Because this, with regard to the bedrooms number. Okay, next. Summarizing, multiple regression coefficient must be interpreted, okay, in terms of the other predictor. So in the case of this one, we interpret bedroom as with regard to the price of the home, okay, fixed for living area, means that the living area is constant. Okay, and regression coefficient should not be interpreted casually. Do not assume causation between the predictor variables and the response variable. So we don't say that because of this particular, where's the equation just now? Um, Not because of this living area is small, then the price is reduced or the price is increased. Okay, so there is no causation cause over here, as we have our discussion with ANOVA. Last time, causation can be interpreted in ANOVA, but not in the multiple regression. So far, do you have any question, class? Do you have any question? Okay, if you don't have any question, let us look at the next example. Okay, interpreting multiple regression coefficient. So in this example, we have ticket prices. On a typical night in New York City, about 25,000 people attend a Broadway show, paying an average price of more than 75 per ticket. So assume dollar, $75 per ticket. Data for most week of 2006 until 2008 consider the variables paid attendance. This is your first IV in terms of thousand. Number of shows, second IV. Third IV is average ticket price. Okay, and to predict the receipt in million. This is your DV. Okay, so these are all your IVs. Consider the regression model for this variable. So you have your dependent variable receipt in million, and you have your R squared 99.9%. So is that a good indicator, class? The, the R squared 99.9%. Is that a good indicator for good model?
Good.
Yes.
Yes or no?
Yes.
Yes.
Yes. Yes, correct. Okay. Okay, hold on. My tab. Okay. So means that having paid attendance, number of shows, and average ticket means that we can explain 99.9% variation in terms of the receipt. Okay, so that could be a simplest way on how you can comment on the R squared. And for the regression and residual, so you can see that the F ratio over here, unfortunately, the p-value is not included. So let us see what is the next discussion for this particular part. Okay. In terms of the F ratio, you need to compare with the critical value for the F. Okay. In this case, we are not going to do that. So just ignore this particular part, and assuming we are concentrating on the model of your IV, whereby we need to find out whether your IV is significant or not to your model. Okay, so write the regression model for this variable. So you can see, sorry, the margin of this particular um, analysis is a bit uh, not really good. So you can see that you have the first paid attendance, you can have the second IV is number of show, and the third one is the average ticket price. And the coefficient for paid attendant is this one. For number of show is this one. And the average ticket price is 0.24. And all the coefficient is positive in value. Okay, so everything means that each and every single IV increases the receipt of this particular uh, model. Okay, and you can see that the T ratio, how further away it is from the zero value. And if you can see from this particular P value, paid attendance is 0.0001, number of show is 0.116, and average ticket price is 0.0001. So which of these independent variable is not significant? Which one of the IV is not significant? Class, based on this particular p-value, which of the IV that is not significant to the model? Look at the p-value, class.
0.116.
Yes, means that this particular variable, number of show, okay, seems not significant to the receipt, okay, to the receipt in million. But in terms of calculating all these three variables into the model, it gives 99.9% in terms of the R squared. Okay, so even though the R squared is high, you can see that the contribution of each of the IV may not be similar for each. And we can see that in this particular case, number of show is not significant. Okay, so let's go back to the question just now. Write the regression model for this variable. So if we use the actual DV and IV, so receipt in million is equal to negative 18.32 is the interception. Okay, so negative 18.32 plus the first coefficient of the paid attendance is 0.076. And for the number of show is 0.007. And for average ticket price is 0.24. So that will be your what we call estimated model for this particular example. Okay, now interpret the coefficient of paid attendance. Paid attendance. Look at the paid attendance. Look at the paid attendance. First, you can see that the paid attendance has positive coefficient. Okay, positive coefficient. Now, how do we interpret? Okay, after the number of shows and ticket price are accounted for, after the number of shows, we are talking about the interpretation of paid attendance. So, we are putting the number of show and average ticket price accounted. Sometimes certain books said as fixed. Okay, sometimes certain books said as fixed, sometimes constant. They are almost similar in terms of the meaning. So after the number of shows and ticket price are accounted for, okay, means that we account this number of shows and average ticket price. Okay, an increase of 1,000 customer. If let's say we have 1,000 customer, so 1,000 customer, what happened? 1,000 customer means that 1,000 times 0.076. So you will get 1, 2, 3, 1, 2, 3. So you will get what? 76. So in terms of the average, so let's say I don't want to put into, so okay. Now, with 1,000 paid attendance, what happened is that it will increase. It will increase because of this particular positive value. An increase of 1,000 customer generate an average increase of 76,000 in receipt. Okay, so imagine 76,000, 1,000 ticket. Okay, so you will get in terms of the average increase in the receipt, you will get 76,000 in terms of considering for 1,000 here over here. So paid attendance 1,000, it will give you an increase of 76,000 in the receipt. Imagine this one is in million. So in million means that you have 60 over here. So that's why you have 76,000 over here. Okay, so estimate receipt when paid attendance was 200,000. Estimate receipt when the paid attendance, okay, when the paid attendance 200,000, okay, attending 30 show. So you have 30 show over here, okay. An average ticket price of 70. Okay, so you will get 13.89 million for this particular estimation using this particular model. So that is how you can interpret the what we call on the receipt in terms of million. So is it likely to be a good prediction? Yes, because of the R squared is very high, almost 100. So this model explains most of the variability in the receipt, even though the number of show is not significant, which is less than 0.05. Okay. So can we have a rest, class? I need to take some water. So I will just continue afterwards. Okay, class, let us continue. Okay, now for this particular calculation, I'm looking for my pen. Where is my pen just now? Hold on, Oh my goodness. Okay, I'm really sorry. Okay. For the calculation just now, so how do we get 13.89 thousand? Okay. So if we include into the equation, okay, we have the equation of receipt is equal to negative 18.32 plus 0.076, okay, multiplied by 200,000, okay, and attended for 30 shows. So it will be 0.007, and the number of show is 30. And then you have the last one that will be on the average ticket price, that will be 0.24, okay, multiply with the average ticket price is 70. Okay, so can you calculate that, class? Can you calculate that? What do you get? I get other than 13.89 million. So I need to check with you. So if it is incorrect, so I would like to um make a correction to the cost coordinator. Okay, if I'm not mistaken, if I calculate this, it will get 15, okay, 15 million 19869, because the receipt is in million. Okay, so it will be 15.19 million, not 13.89. I will check this one. Why is that so? So is it a good prediction? Yes, based on the R squared. Yes, it is a good prediction, since shows that 99.9% is being explained by this particular model. Okay, so do you have any question here, class? Do you have any questions? Okay, if you don't have any questions, let us move to the assumptions and condition for multiple linear regression or multiple regression model. So as usual, if we have assumptions in ANOVA, we have assumption in simple linear regression, we do also have assumption for multiple regression, and we can assume, you can imagine that the assumption will be much complicated because we have more variables included in the model. Okay, so the first assumption would be the linearity assumptions. So for the linearity assumptions, I think for you, we just give you the what we call the description on how the linearity or the rest of the assumption can be checked or can be visualized based on the whatever um, explanation we have in the slide. So if we want to go further in terms of the discussion, there will be more on the part that we have to include in terms of explaining on the assumption of this particular model. So let us make it simplified for you. For the simple linear regression or for the multiple regression, the first assumption, it need to be linear. Okay, for the linearity condition, okay, we have to check each of the predictors against the response variable for the linearity. Means that you have to check for, if you are talking about the price or the receipt over here, the receipt, you have to run for, the first is the, what was that, the first one, paid attendance. Okay, the paid attendance, so you have to run one by one. Paid attendance, and then you have to run for receipt and the number of show. In real discussion, when we figure out that the independent variable or the predictor is not significant, we will exclude from the model. But in this case, we just remain as it is, because considering that you are still in a first semester of your study. Okay, and the last one would be receipt with what we call in the average ticket price. Okay, ticket price. So in the case of the home price and the living area and the number of bedrooms, okay, so you will have to plot with the price and the living area, okay, and the since the for the living for the bedrooms, you have different option of bedrooms. So in this case, you have to check for this particular each and every number of bedrooms that you have. Okay, in terms of the what we call based on the box plot. Okay, so in this case, in terms of the price and living area, we can somewhat like say that, okay, this is merely like a linear. Okay, but for the price and the bedroom, okay, um I'm not sure how I can explain this particular box plot with regard to the linearity of this price actually, because box plot may not be useful for interpreting the linearity of a variable. But in this case, I'm not sure why it is included in terms of the box plot versus each number of rooms that it has for that particular house. So in this case, never mind, just take it as it is. So for one bedroom, you can see that the variation is very small compared to two bedroom until five bedroom. As we increase the number of bedrooms, we have the variability for each is increasing actually. Okay, but somehow in this case, it mentioned that linearity condition is satisfied for both bedroom and living area. Okay, so as for now, take it as it is. So for the living area and price, this is clear cut right away. But for this particular price with regard to bedrooms, I will need to check and I will let you know later why and how we can identify based on the side-by-side box plot. Okay, but in the case of this particular example, we know that the linearity is considered fulfilled. Okay. Now, for the linearity assumption as well, we need to check with the residual. Okay, the residual is actually obtained for, if let's say you have your data last time, this is your actual data. We are going to measure this error. Okay, and this error is actually the one, okay, that is plotted over here. And that is why you can see that over here, the what we call the horizontal line, okay, is based on the 0 price over here, and we may have what we call the below and after, below and above of this particular residual value based on this measurement that we have over here. Okay, so if in this case you have somewhat like this one, okay, this one is considered satisfied in terms of the linearity. You cannot have this particular form of, let's say this 0 is over here. If you have somewhat like this form, okay, so you can see that it is forming like increasing in terms of the as we increase the predicted value, okay, the variation or the residual become larger. So this is not linear, okay, obviously. So if you have this somewhat like this one, okay, we can say that there is no pattern, obvious pattern appeared in your residual plot, okay, no obvious pattern, okay, appear. So means that linearity is fulfilled. If you have this one, this is what we call as pattern exists. So it is not linear. Okay. So sometimes we may have somewhat like this one. Where do I? If let's say you have 0 over here, if let's say you have somewhat like, you can have what we call as, if you draw, it will somewhat like quadratic equation. Okay, so this one also pattern. Okay, and this shows that the model is not, the variable is not linear. So pattern exists, not linear. Okay, class, do you have any question here? Okay, so for the next one, independence assumption. So as usual, there is no way to be sure the assumption is satisfied, but think about how the data were collected to decide if the assumption is reasonable. Okay, so if you are talking about the independence assumption, okay, means that you have to think back on how the data were collected. So if you are the one that do the data collection, you know the real situation on how you collect the data, and in terms of the dependency and everything, you may know about that when you did the collection. Okay, in terms of the randomization condition, does the data collected introduce any bias? Means that if you have your population over here, for example, this is your population. Okay, if you are talking about I'm not sure in this case, if I want to take the example of home price and bedroom, we are not talking about the specific types of respondent. Just in case, for example, I bring you back to the example of diabetic patient. If you are talking about diabetic patient, so you are talking about diabetes patient over here, you are talking about diabetes patient that you should collect and represent the whole population of your data. Okay, if you are collecting data under per list, for example, okay, so means that you need to identify your sample over here is representing per list per se. Okay, means that you cannot take a diabetic patient that is located in Arau only, and you do the analysis and make the generalization, it is for Perlis. Whereas you are only include patient from Arau only. So this is what one example of what we call as bias. Okay, so we need to make sure that the data is generalized to the whole population included in your uh, analysis or in your research. Okay, so that will be for randomization condition. And for the equal variance assumption, so I think this one is just kind of repetition that we have last time. We have to make sure that the variance are equal. And when we said variance are equal, we said that the distribution of the variance must be somewhat similar from one another. Okay, so in the case of this multiple regression, equal variance assumptions means that we need to go and check on the equal spread condition. So the variability of the error should be about the same of each predictor. So variability of error for each predictor. So if you have 5 predictors, you should have about similar what we call variability of error in your predictor, in each and every predictor that you have. So if you have somewhat like similar for each predictor, then equal variance would be satisfied. Okay, so in the case of this one, still we are using the residual, means that we are taking the error terms from the plot of your scatter plot with the predicted line, and we put this into the what we call as the residual plot. Okay, so in this case, we are looking at this particular what we call equal spread condition. So as I mentioned just now, so you have the line 0 over here. So you can see the above what we call the above distribution and the below distribution are almost about similar. So in this case, we can assume that the equal variance assumption is fulfilled. Okay, then the third one. So this one is the first one, linearity. Okay. Second is the independence. Third is the equal variance. And number 4 is the normality assumption. As usual, we need to make sure that our data is normal. Okay. My goodness. Okay, hold on. Okay. How I log? Okay. How do I log this? Never mind. Okay, I'll just make sure I didn't. Okay. So the next one would be the fourth one would be normality assumption. So as usual, it should be normal. Okay. And this normality can be observed if you use your histogram for the residual, again for the residual, and you can see that you should have one unimodel. Unimodel means that you have only one peak. Okay, one peak only, and it should be symmetric. Nicely symmetric means that you have this particular form of your distribution. Okay, so that would be normality. But in terms of the plotting this particular plot as what you have in your Excel last time, and I did not explain on that. So you will have this particular what we call a residual plot that shows the normality of this particular independent variable. So in this case, home price example. So in this case, home price and the tail of the distribution appear to be non-normal. So in this case, the tail over here represent the tail over here. Okay, so you can see that over here, you can have a bit of tail, and it shows that it is not normal in terms of this particular data. Okay, so the next one, I think overall there will be 4 assumptions. And then if I go to the summary, okay, what you can do when you want to model your multiple regression model and the conditional check, okay. First, check the linearity condition which with a scatter plot for each predictor. If necessary, consider data re-expression. But just focus on this. Okay, do the scatter plot. Does your scatter plot shows linear or non-linear? That would be the easiest one. Then If the linearity condition is satisfied, fit a multiple regression model to the data. Once you have checked the linearity, then only you can model, okay? And then find the residual and the predicted value. So everything will be calculated based on your software. So everything will be done automatically. And then inspect the scatter plot of the residual against the predicted, check for the patterns and equal spread. This one is for the assumption of this one, okay, for the linearity assumption. And then number 5, think of how the data were collected. Do you expect the data to be independent? Okay. Was suitable randomization utilized? Are the data representative of a clearly identifiable population? Is autocorrelation an issue? So this one I think is uh to the discussion is not really in that, but as for now I'll just leave it as it is. Okay. Now, the last that would be you need to check is the condition check. Feel free to interpret the regression model and use for prediction. If everything, the R squared value is very high, and then all the variable is significant, so then you can proceed with the checking the what we call the coefficient, so that you can interpret the coefficient for the particular model. And check the nearly normal condition by inspecting a residual distribution. That would be the last part of your checking just now over here. Okay. And that one is everything done by your software. Okay. So that would be on the assumption. Last but not least, on how we can do the testing of the multiple regression model. So I think that one will be halfway from the whole slide that we have for this particular multiple regression. Okay, I think there will be few more slides that I need to explain based on this particular model. Okay, so just remember back what we have when we have the discussion under simple linear regression, on how we can check whether our simple linear regression is a good model. And if it is a good model, we can proceed with the prediction part. Okay. If the model is not being checked whether it is a good model or not, don't do the prediction yet. Prediction can only be done once you have identified that the model is good enough for you to use. Okay. So in the case for multiple regression, we are talking about K independent variable. So in the case of K independent variable means that for the null statement, we will have to check whether beta 1 is equal to beta 2 is equal to beta K. So this will be your first null statement. And the alternative statement will be at least one of beta I, where I is equal to 1, 2 until K. So at least one of the beta is significant. Okay. So in this case, this one, you can imagine that the model is not significant. No relationship between beta I and the model and the dependent variable. Okay. So we test this hypothesis with an F-test, a generalization of the t-test to more than one predictor. So if you are talking about one predictor, you use t-test. If you are talking more than one predictor, then we are going to use the F-test. Okay. So in terms of the statement of hypothesis, it's just that you add more beta in your statement. That's it. Now, for the F distribution, okay, so F distribution have two parameter. Okay, the first parameter would be the K, where K is the number of predictors, your IV. Okay, and the degree of freedom, okay, this one is the degree of freedom, is the N minus K minus 1, where N is the number of observation. So if your sample size is 100, then 100 minus k minus 1. If let's say k is equal to 3 variable, so means that 100 minus 3 minus 1. So you will have 96 in terms of the degree of freedom. Okay, so that would be on F. Yeah. So the F test is one-sided. So if you still remember, when I explained about ANOVA last time, F test is somewhat like chi-squared. Okay, we begin from 0. Okay, so when we make decision, remember back when we have our alpha. So let's say this is your alpha, your rejection region. Okay, so your rejection region in this case, okay, so this is your FCV. Your FCV would be F K N minus K minus 1. So this will be your critical value, and should be another one that will be alpha. Okay, so that will be your what we call F critical value. So your F critical value can be, we can make a decision by comparing with the F test. F test is your calculated F. So your calculated F is your F test. So it can be either in this form or in this form. So if it is in this area, then we reject. If it is in this area, then we fail to reject. So what happened? Okay, since F test is one-sided, the bigger the F value means the smaller the P value. What does this mean? Imagine that this is your F test, your FCV. This is your FCV. So this is your FCV. Okay. The bigger the FCV, because this is 0, if we move on over here, your F will be increasing in terms of the value. As we move over here, okay, the rejection region also become small. Okay, so in the case of in the case of what we call rejection region, this is the case based on the FCV. But if you are talking about the calculated F, if your F test is bigger means that what? Bigger means that the location will be on the tail of this particular F distribution. The bigger the F test, the smaller the P value. Why? Because the P value is okay. This is your F test. F test bounded the P value. So this is your P value. So this is your P value. Where is my alpha? My alpha is over here. The whole area of this is my alpha. Okay? So that is why the bigger the F, the smaller the P value. The smaller the P value, the easier for us to reject the null hypothesis. Reject the null hypothesis means that, okay, you have at least one of the beta I is not equal to 0, means that the model is significant. Okay, so if a multiple regression F test tend to a rejection of the null hypothesis, then check the t-test statistic for each coefficient. Since this one is actually based on the theoretical part, so I'll just go through very quick. Later when we have example, we can have more detail or further discussion on how we can what we call implement this particular steps. Okay, so when we test, okay, we need to check for the t-test for each of the coefficient. Means that if you have beta I, where I you have until k, so you need to check one by one. Okay, so that's how it can be done for multiple regression. Okay, so for the confidence interval for each slope, which is for the beta, okay, you will have this particular what we call confidence interval. So this is your value of your beta, okay, and this one is your what we call margin of error. Okay, last time we did discuss on this, but not really in terms of the confidence interval also is discussed a bit on the mean. Yeah. Okay. I think for the last part, okay, the tricky part of the F test or the T test, okay, the standard error are hard to compute. Okay, but definitely the software will compute for you. So the meaning of a coefficient depend on whether on the other predictor in the model, as we saw the home price example, if we have only the number of bedrooms, and in addition to number of bedrooms in terms of the living area uh, square foot. Okay, so in the case of we fail to reject null, okay, if we fail to reject null based on the t-test, it does not mean that the xj has no relationship to y. Okay, so means that the xj contribute nothing to modeling after allowing for the other predictors. Okay, so we have to look at, I think this one will be much easier if you have example. Okay, on the theoretical part. Okay, in multiple regression, it looks like beta j tells us effect of its associated predictor, but the coefficient beta j can be different from zero, even if when there is no simple linear regression between y and xj. Okay, so um, uh, what does it the main point in here is that, okay, when you add new variable into your model, okay, the slope may change in sign. It will be based on how the relationship between the variable included in the model interact to each other in terms of predicting the y or the dependent variable. Okay, so let us look at the ticket prices. Okay, for the ticket prices, in this case, we have, I think, similar situation of what we have just now. Okay, we have the R squared is 99.9%, shows that we have the paid attendance, the number of show, and the average ticket price is giving a good what we call a good indicator to predict the receipt for this particular uh, show. Okay, and based on this model, okay, based on this model, we can see that the p-value for this particular model. So when you see regression and residual, this one reflect the test for the. Okay, so please make sure you understand when you have the analysis output, you know what does that output refers to. So in this case, when we see the model over here is p-value is less than is 0.0000, less than 0.0001 means that it is small, even smaller than 0.0001. Okay, so in the case of alpha, if alpha is equal to 0.05 or even smaller, alpha 0.001, okay, 1%. This is 0, okay, 1%. Okay, even smaller, you can see that if let's say this is the F test, and your alpha is over here is alpha is, let's say, is 0.01. Okay, by having alpha 0.01, your F or your F test or your P value is even smaller. So over here is your p-value. So this is your F test. And this one is your FCV, critical value. So we reject the null hypothesis. Okay. So we can say that the model is significant. Okay. So in this case, if we put in order in terms of the coefficient, the testing the coefficient value for beta 1, beta 2, beta 3, we can see that um, I'm not really keen of this particular, the way of it is being written. I would prefer at least one beta j or beta I is not equal to 0. Okay? We don't know which one. It could be 1, it could be 2 that is not equal to 0. It could be all of them are not equal to 0. So the interpretation over here is kind of misleading a bit. So if let's say this is your model, okay, we have three independent variable. So F statistic is the ratio is 18,634 for in terms of the F ratio. But if we are talking about the p-value is less than 0.001, which is smaller than the alpha. So what can we draw in terms of the conclusion? Since the p-value is small, we reject the null hypothesis. At least one of the predictor accounts for enough variation in Y to be useful. So this is how you can interpret in terms of the test, hypothesis test. Okay? Now, next. We will finish until, I think I will just finish until this part. Okay, the question one, I think I will discuss after we have an example to discuss with regard to this particular example. Okay, in terms of the exercise in class. Okay, since the F ratio suggests that at least one variable is useful predictor, so we don't know which one. Okay, based on this, at least one of these beta I is not equal to 0, but we don't know which one, right? Okay, next, we need to check. Okay, determine which of the following variable contribute to the presence of the others. Okay, recall the variable paid attendance, number of show, average ticket price to predict receipt in millions. So as you can see over here, you can have the first variable, paid attendance. Second variable, number of show. Third variable is your average ticket price. C for each of the p-value. Okay, this one is significant. This one is not significant. This one is significant. Okay, so how do we suggest this model? Okay, since F ratio suggests at least one variable is a useful predictor, determine which of the following variable contribute to the presence of others. Paid attendance and average ticket price. Okay, paid attendance and average ticket price. Okay, contribute even when all other variables are in the model. So this is how we can what we call comment in terms of the usefulness of this particular variable into the model. Okay, number of show, however, is not significant. P-value is 0.116 and should be removed from the model. Once removed, rerun the model, okay, to determine if the remaining two predictors are still significant. So this is another question mark. Whenever you remove this number of show, it's either both are still significant or could be either one may not be significant or maybe worst case scenario, both are not significant because we don't have the third variable included. So that could be what we call uh, a mystery if you don't run your model when you have some of the or one of the IV is not significant, and if you don't rerun the new model without the insignificant variable, you may not see what happened to your new model. Okay, So I guess for this one, I think later on for the next class, um I will try to get one more equation that we can do in class, so that you can have the experience solving the questions using the Excel, and generate the multiple linear regression or multiple regression using the Excel. Or if you wish to use your SPSS, you can also use your SPSS. So class, I think for our next discussion on how to analyze, uh, Excel can give you analysis for multiple regression. So if you wish to use Excel, I think for now you can just remain using Excel. For some of you who have already downloaded your SPSS, you can proceed with your SPSS. Okay, I'll try my best to get my SPSS installed to my laptop, because I will having my leave until Sunday, since I will be driving back from Nilai, Kuala Lumpur, from Kuala Lumpur to Kedah on my own. I may not be able to install my SPSS for the class. Worst case scenario, I will just show you on how to use your Excel, on how to uh, do the exploratory data analysis, especially on how you can begin with your aggregating your IV based on your items that you have. Okay, so please get ready with your data. I think the easiest one, please make sure your data is ready in your Excel. And maybe once you have got your data in your Excel, it can be exported to SPSS easily if you wish to analyze using SPSS. Okay, so I think that's all for today's class. If you have any questions, you can remain from the in the group. So the rest, if you don't have any questions, you can dismiss. Thank you very much for tonight class. So tomorrow we don't have any class. Yeah. Thank you. Assalamualaikum and a very good evening. For those who have any questions, you can remain in in the online class. Anyone who got any questions? Otherwise, I'll just finish.
Mm. No,
Yes.
madam. Thank you.
Okay, thank you.
Thank you, madam.
Thank you, madam.
Thank you, madam.
Thank you, madam.
Yeah, thank you. Okay, I will just on off the video. Thank you.